Hello, everyone. I'm Paul Drabble, Global Marketing Director at Delta Q Technologies, a member of the Zappi Group of companies. I'd like to extend a warm welcome to everyone tuning in today for this next session, Maximizing Onboard Charger Power Density, Innovations in GaN, SiC, and Advanced Cooling. It's my pleasure to introduce our speaker, Mr. Chris Botting, who is the Manager of Research at Delta Q Technologies. Chris has over 20 years of experience in energy storage, power converters, and electric vehicle powertrains, and is responsible for research, university collaborations, intellectual property, and Delta Q's battery test lab. Before we begin, if you have any questions during the session, please add them to the Q&A tab to the top right of your webinar screen. And note that your questions will be sent privately. I'll now disappear behind the scenes and will chime back in at the end to facilitate a brief Q&A at the end, answering audience questions in the order they were received. With that said, I'd like to hand off to Chris. The session is now yours.
Great, thanks, Paul. As the title says, I'll be talking about how to maximize the power density of onboard chargers. Looking at the agenda, we'll be starting with briefly looking at what is the motivation, why do we want to increase power density, and then look at some of the bottlenecks and the challenges, what are the obstacles, and what are some of the trade-offs in the design. And then we will dive into more of the nitty-gritty of how to actually go about getting higher power density from a cooling, mechanical, electrical, and a system integration point of view. And then we will finish up with some real-world data and examples and trends in the industrial EV charger space and some takeaways. So what I'm hoping that you take away from this talk today, particularly if you work on the design side, is to get a deeper understanding of what goes into power converter design and what are some of the trade-offs. And then the second point maybe is more broadly useful if you're a purchaser, if you're involved in the design or the integration of systems which use onboard converters, to understand what are some of the trade-offs that you can make in the design and the specification of your system, which can impact real-world power density. So let's start with why onboard power density. So fairly obviously, you can make chargers smaller, or you can increase the power in a given space. So starting with the first one, decreasing size and weight. This is largely about increasing the range and the payload of a vehicle. If there's less space and less weight taken up by the electronics, then there's more room either for the payload or for the batteries to increase range. And on smaller machines and vehicles, 2 and 3 wheeled vehicles, that kind of thing, this can also start to enable new, package types and new vehicle types. If you can really shrink everything down and have more flexibility as the system designer. It may also be possible to move a charger from offboard to onboard. The motivation for increasing power is also pretty straightforward. Faster charging, bigger batteries. Faster charging can mean less downtime. There's less time that the vehicle can't be used. In some applications, slow charging in the past has led to battery swapping. So you've got multiple battery packs per vehicle or machine, and that isn't necessary if you can charge fast enough. Much of this really is driven by the larger trend of lithium-ion batteries. So as you all no doubt know, lithium batteries have made huge strides in the last couple of decades. Their cost has come down significantly, and their power density has increased. Their energy density. I'm particularly looking at the battery pack level. So this is not just cells getting better, but also battery packs getting better at packing the energy in and having less wasted space. Relative to lead acid, you can see that lithium is reaching the same prices as lead acid. It's much more dense and it can charge much faster at maybe like a 1 hour rate versus a 4 hour or 8 hour rate for lead acid. So that's part of a larger macro trend that as the batteries get bigger and faster charging, then that leads to a demand for higher density, faster chargers. The power electronics have to keep up with the batteries. So what are some of the obstacles to that? Let's start at the system level. Maybe one of the most obvious challenges or bottlenecks is that you can only get as much power as where you plug into AC. So if you're plugging into a residential outlet, that's say 120 volts in North America, or limited to say 10 amps, 12 amps, then you're going to be limited to 1 or 2 kilowatts of charger power. So the solution here is pretty straightforward. As you need more power, you need to first increase the voltage from 120 to 230, 240, start to increase current, from 15 amp breaker, 20, 40, up to 60 amp breaker to get up to, 3, 7, 10 kilowatts. And then finally, when you start to be limited by the currents, then you need to start increasing the number of phases with a 3-phase AC. I've shown this as topping out at 22 kilowatts, which is where things typically top out in terms of industrial outlets and EVSE AC charge stations. It's possible to get higher power, but it starts to be specialized outlets. So the solution is pretty straightforward, but there is now a trade-off. If you've got a higher power charger, you can't just plug in anywhere. Similarly, the DC output can also be a bottleneck. As the power goes up, so does the current. And so the issue there is that DC current heats the battery, heats the cables, heats the connectors. So there are limits. There are practical limits to how much current you can put into a battery or into a system. Adding copper increases cost and weight, and it's hard to meet the challenge just by adding copper, because losses increase as the square of the current, and copper is very expensive and heavy. This is why DC fast charge cables at the higher power levels tend to be liquid cooled to keep the weight and the flexibility of those cables down. But even there are practical limits. Several hundred amps, maybe up to 1,000 amps at the absolute most. But at a certain point, you'll want to increase DC voltage. So in the industrial space, that usually starts at 24 volts, 36 volts for smaller class 3 forklifts and so on, up to 48 volts, 80 and 96. These are the traditional lead acid battery voltages, but there are lithium batteries also operating in that space. And then there's a huge jump from about 100 volts to 400 and 800 volt, really not much in between, as you start to need, in particular, faster DC fast charging. Here again, it's a solution, but it also has trade-offs. As you increase the voltage, you've got shock hazards, you've got things you need to do with high voltage interlocks and safety and fingerproofing and so on. The other major bottleneck really is getting the heat out. So you have enough AC supply and you have a sufficient DC output voltage and so on. But if you're going to take a power converter and shrink it smaller or put more power in that box, you're putting more loss heat in less space, which makes it more challenging to get the heat out. Any sort of heat exchanger or heat sink surface area, well, that also takes up space and makes it hard to shrink chargers. So the solution here is to increase the cooling capacity. First moving from passive air cooling to fan cooling, then to liquid cooling where there's more heat capacity in the medium, And finally, probably not needed for onboard battery chargers, but maybe for high performance motors and batteries, you can get into making use of active cooling with a refrigerant cycle. So this again is a solution which can increase power density, but it also has drawbacks. You increase cost and complexity. At the far left, it's really nice having a system that has no moving parts at all. Once you start adding fans that have to be sealed and dustproof, once you start adding external liquid cooling systems that have their own weight and cost, that increases the complexity of the system. So that's it for the bottlenecks on the system side, but then there's the actual converter itself. So this may seem obvious, but a higher power converter is a larger converter. So how do you fit more power into the same box? The solution isn't going to be a single bullet point. That's what we're going to spend most of the presentation talking about, but it's complicated, but it is possible. So here's one case study from a first generation Volkswagen e-Golf onboard charger. What you see on the left was the first generation charger, which was 3.3 kilowatts. On the right is the second generation. They doubled the power to 6.6 kilowatts. And that's in basically the same box. So doubling the power density. Now, how did they do that? We will circle back to this at the end of the presentation, and I will let you know. But first, maybe some of you are asking this question: why can't we just add SiC or GaN? It's right there in the subtitle of this talk, and we actually heard a presentation earlier this morning from a semiconductor supplier talking about silicon carbide and GaN. We've probably all come across GaN in USB chargers for electronics, and there's some claims of very big size reductions. I've pasted in one here that's like 50% smaller, but you can find other percents that are equally impressive. What these typically don't answer is how much of the cost increase. How hot is it running now relative to the original charger, and then what is the impact on the reliability, largely due to it running hotter. And in a consumer application where you're talking about having a $20 charger double in cost and run hotter and maybe last a year or two less, a early adopter in a consumer sort of an application is going to be willing to take trade-offs that a industrial user might not. So yes, the so-called wide bandgap devices, SiC and GaN, they do have real benefits. They can definitely switch faster. They can switch with lower loss. The key really is how is that being used? Given the extra cost, given the complexity, given maybe impacts on EMC, on the switching noise, how do you use those devices in a way that has the most benefit and the most bang for the buck? There are other challenges. I'm not going to go into it, but lots of other trade-offs. We're designing for EMC. We need safety and regulatory approvals. We're selling global products that need to go into multiple countries and markets. They need to be designed for manufacturing and sealed, and there's all sorts of things about durability and feature set. So there's lots of trade-offs that have to be considered. So let's dive into some of the details, though. On a technical level, what are the options to actually increase onboard charger power density? Which basically is, how do we shrink the volume? A simple way to view a power converter, particularly a sealed power converter, is to think of it like a box full of blocks. So there's different things you can do. On the mechanical side, you can try to pack the blocks closer. Maybe you pack them in a more space efficient way so that there's less airspace in between them. Maybe you can stack them. Maybe there are ways of making all the blocks have similar sizes and flat sides so that there's less wasted airspace. From a electrical point of view, that's usually looking at how can you shrink the blocks or shrink some of the blocks by doing things like increasing switching frequency. There's system integration. If you start to integrate multiple functions into a charger, then are you able to delete blocks? Can you do more functions with less blocks? And then cooling, the analogy breaks down here just a little bit, but this is more like shrinking the walls of the box, shrinking the lid. The cooling solution isn't inside the box; it's outside the box, whether it's a fan-cooled heatsink or a liquid cold plate, and that also occupies space. Cooling can also help you to get things closer together. Cooling can also help you to shrink the blocks. Really, it's the key to many of these other design options is starting with, as you make things smaller, pack them closer together, how do you get the heat out of this box? So what's actually taking up the space? I've got a example here from a design that we recently analyzed with our team. We've been looking at higher charger power density for our future products. So we started with some known designs and analyzed them in terms of like where's the volume actually going. What may jump out at you is that the actual power converter is somewhere between a third and a quarter of the volume here. So cooling is a third. That's the heat sink. This is an air cooled charger. It's already fairly compact inside, but there's a sizable heat sink, fan, and shroud. Empty space. This is a debatable category, but there's a lot of airspace which is not being used, both inside and outside of the box. If you compare it to like the maximum length, width, height. The housing itself, the walls and the shape and the mounting feet, connectors, that occupies a lot of space. And then you're left with like about a quarter of the volume is actually the power converter itself. I should say that I've actually counted some space in these categories. So just because space is empty doesn't mean it's always not serving a purpose. Often we have to have certain creepages and clearances for safety and regulatory for live parts, or have shielding that sits between things to prevent crosstalk. But I've factored that in roughly into the packaging claim here. So looking at that smaller portion, which actually is power converter, the biggest thing is the magnetics. So this is wire wound transformers and inductors and filters. The caps are also a significant size. And then actually one of the smallest things is the actual power semiconductor devices. Often the semiconductor devices, the MOSFET switches and the diodes are the first place people look to shrink a battery charger. They're actually not occupying much volume in and of themselves, but they have the ability to drive the volume of other things by decreasing the amount of cooling which is needed, decreasing the size of the magnetics, etc. But I find it helpful to start with a holistic view of what is actually taking up space, because it gives you some idea of what the potential is, what's going to be possible. For instance, I've seen chargers that have deleted the AC input relay. So rather than having a mechanical relay, they have a active bridge rectifier. There may well be reasons to do this from a reliability point of view, or in terms of wanting to have direct control of the AC inrush current. But it's not likely increasing power density if that AC input relay is only 0.1% of the total charger volume. So that would be looking at something where from the first order, you can already tell it's not going to have a lot of impact on increasing power density of the total charger. So thinking more about that big picture, in some industries, particularly software, there's often, when brainstorming or trying to prioritize new features, they're often looked at in terms of impact versus effort, which you can also think of as being cost versus benefit. So on that impact benefit vertical axis, how much can the system volume be reduced? Is it high impact, like you're going to cut the size of the charger in half, or is it low impact, like that, 0.1%? And then on the effort side, or the cost axis, what's the added development time? What's the added technical risk? What's the added hardware cost? The BOM cost? There's different ways of looking at that cost, but generally speaking, you're going to want to be looking for things that first fall into that upper left quadrant of easy wins. Like what are the high impact ways of really decreasing volume without adding a lot of development cost, technical risk, and time. And you want to stay out of that lower right, the money pit, where you're spending a lot of time and effort doing things that aren't actually making a big change. In practice, many things are going to fall into that sort of incremental through big bets. Maybe big bets is a good place for long-term research. And in the incremental, maybe there are lots of small things you can do that will add up to a significant change. So if we look at this from those categories we were talking about, cooling, mechanical, and so on, where do they fall? In our experience, the cooling and the mechanical, particularly cooling, generally is the best bang for the buck, which I think should be clear looking at the relative size of the different parts of a typical air-cooled design in that previous pie chart. There are things on the electrical side that are also worth doing. They're probably smaller gains, but they can stack up. And then finally, on the system integration side, there are actually quite a few interesting things which can be done. They can be sort of bigger bets, like they could have big impact. There's also a lot of technical risk. Those might make longer, research topics, or they could be, you would have to do some advanced technology work on those to be comfortable putting those into a product development program and not having it schedule, go off of the rails. So let's look at these in that order, starting with the cooling. Cooling, I'm talking here about onboard chargers that are sealed and are waterproof, so IP67 typically. So what that means is that unlike offboard unsealed things where you've got a unsealed box where you can blow a fan through and you can directly cool the heat sources, here the cooling is indirect. So you have heat sources in a sealed box, and the first thing you have to do is get the heat from the inside to the outside, and that is through conduction. And that's complicated by the fact that your heat sources are electrically live, and so you can't just connect them to the case. You have to provide some sort of isolation. Once you've got the heat outside, now you have convection, whether it's passive or fan cooling, or it's a liquid cold plate. You're transferring heat by convection to some medium. So looking at those two steps, first, let's start by looking at outside the box first, so cooling. Starting with fan cooling on an external heatsink. There are lots of ways to do this. There are decisions to be made about the fan. What's the type of fan? Is it axial? Is it a centrifugal fan? Is it a blower? How many are there? Where is it located? Is that fan also sealed? If you have a sealed battery charger and then you have an unsealed fan outside, well, that's going to be a failure point. Your heatsink needs fins, so what's their size, thickness, and height? How are they spaced? How are they oriented? They can be, radial, which is what you're seeing in the top right. They can be parallel, as you're seeing on some of those lower chargers. They can be sort of swirled so that they follow the direction of the rotation of the fan. You can have staggered fins, which is what you're seeing there in the middle, where there are some short sort of teardrop-shaped fins that are broken and then staggered to try to promote more heat exchange on the leading edges. Pin fin, which I'm not showing, typically that's going to be lower surface area. If you got a fan, then you may want to have a shroud, which is there's a partial shroud shown on the top to sort of force air to pass through the fins. That could also be a full shroud, which would extend all the way out to the edges, or you could have no shroud. There are certainly trade-offs there with the flow versus the back pressure. And then how is it constructed? Most of what you're seeing there is aluminum casting. That's certainly the most common, but you can also use a extrusion, like you see in the bottom. That has some trade-offs. You're going to need a lot of post machining, and the fins can only be parallel. But with an extrusion, the aluminum is higher density, higher thermal conductivity, and you could have much smaller feature sizes. You don't have the same sort of draft angles, so you get a lot more fins closer together. And then finally, there's surface coatings and machining on these castings and these heat sinks. So at a high level, what you're usually looking to do with a fan-cooled heat sink is maximize how much air is flowing over surface area. So surface area of the fins, that has airflow over it. There are trade-offs there with the back pressure of the fan. If you choke it too much, then you're not going to have a lot of airflow. There are also trade-offs with fan noise, depending on the application. But, from a high level, that's what you're usually looking to do is where do you want to dump the air? Where are you drawing in cool air? And how can you maximize airflow through as many fins as you can? Moving on from fan cooling to liquid cooling, this is usually more compact. Cooling is usually less of an issue at this point because it's just much, much more effective at moving the heat out, but there are still considerations. So again, you've got some passages. Are there any like flow guides or walls like you're seeing in the upper right that are designed to maintain a certain laminar flow? What about bends or constrictions that can cause, back pressure? How is it constructed? So casting is the most typical. That's what you see in the top right. But it's also possible to do this with a bent tube. So that's what you're seeing in the middle there, a tube that's been bent into a shape and then pressed in, glued in, somehow held into a cavity in a cast housing. This constrains the shape of the coolant passages, but it also makes it easier to make sure that it's not going to leak, that you don't have issues with the density and the porosity of the casting, for instance. It's also possible to do something similar where you take a bent tube and you actually do some sort of an insert molding into a casting. And then finally, you can also make cold plates that are stamped. What you're seeing in the bottom right is a zoom in on the Tesla Model 3 charger, which is made more like radiator fins. So there's some stamped sheets, which are then brazed together to give a very uniform and low profile flat cold plate. Generally speaking, what you're trying to do here is minimize the pressure drop at a high flow. And what I mean there is that a liquid-cooled onboard charger is usually not what the liquid cooling system was designed for. If a vehicle or a machine has a liquid cooling system, it was probably designed and sized to cool larger loads like the traction motor and the battery pack. Those can be very high power, so it can be quite a high capacity system, typically quite high flow rates. And then the battery charger may be sourced later and sort of plumbed into the system as an afterthought. Often that means that the flow rate through the battery charger is much more than is needed to actually get the heat out of the charger. But the main goal is to have large coolant passages that have few turns so that you can minimize pressure drop in the system as a whole. What you're seeing there in the middle bottom is something quite different. So this is in I believe a Tesla Model 3 motor drive, traction motor drive, where they have very high thermal density. So you've got silicon carbide FETs there that are closely coupled to the coolant passage, and they've actually added lots of these pin fins to increase surface area and maximize heat transfer. That's not usually the approach that's needed in an onboard charger, just given its power density. So that's cooling on the outside. Now we move to the inside of the box. So, keeping in mind, we've got live components that need to be electrically insulated, but thermally conducted. So that, usually starts with looking at insulating materials. So most materials tend to be electrical insulators and thermal insulators, or electrical conductors and thermal conductors, like metals, for instance. And on the other side, plastics are usually good electrical insulators, unfortunately also thermal insulators. Ceramics kind of break the mold here. Ceramics tend to be good electrical insulators and can also be quite good thermal conductors. So often alumina or aluminum nitride are used. You're seeing alumina in the upper right with those white sheets. That can be put in place with through-hole devices, as is seen here. Typically, it wouldn't be screwed together like this because that would not pass. That might violate the isolation which is needed. So there would probably be clamping systems, but ceramics are a good tool here, and they can be quite low cost. Main issue being that ceramics have quite a hard surface. So typically thermal grease or some sort of a thermal interface material or paste is needed in that joint. Thermally conductive plastics. So I said, like if you look at that white plastic shape in the lower middle, ceramics can be cast into more complex shapes, but it's difficult because of how they shrink. It's easier to fire them as just simple sheets. And if you need a more complex shape, plastic's going to be the way to go. But plastic's not a good thermal conductor. However, there are thermally conductive plastics that have additives. Usually it's ceramic powders or graphite powders that will increase thermal conductivity while still staying electrically insulating. And also thermal interface films and gap pads. So films like you're seeing in the lower right, these are usually some sort of plastics like Kapton, polyamides and different plastic materials, which can have, they're very good electrical insulators. They're quite poor thermal conductors, but if you can make these films thin enough, then you can still get a lot of heat through them. So that works best for components that are flyer. What about more complex wire wound components like transformers and inductors? Well, what you're going to more likely do is use a thermally conductive potting. So here's several examples. There's a Kia Hyundai charger in the top. That's a transformer that's been held up in a cast box. And if we were to take off one of those black plastic covers, you would see some soft pink silicone that's been cured in place. Bottom right is Tesla Model 3 charger, and bottom left is, I believe, the Chevy Bolt onboard charger. And all of these, you've got transformers and inductors that have been dropped into extruded or cast aluminum boxes, and then, with a few millimeters of gap, which is then filled with a thermally conductive silicone potting material, which does the electrical insulation, thermal conduction, and it can also act as a shock absorber for shock and bind. Polyurethanes and epoxies can also be used. Some of these will be harder, some of them will flow better. And then these can be, oven cured with UV light, or even a room temperature vulcanization, so it doesn't take, it just cures on its own as you squeeze it out. One other thing here, not really a potting material, but also silicone, is that you can get pre-cured silicone gap pads, which can be inserted on surfaces, and you're seeing a couple of those in the upper right photo. Those pink areas are going to be probably pre-cured gap pads that have been cut and then put into place. So cooling, from there we'll move on to the mechanical side. Obviously this is highly linked to the cooling, but what is the best way to fill the 3D space? And Tetris, I think, is really a good way of looking at this. How do you fit all the blocks? How do you not have wasted airspace? Well, one of the things that you can do is take your printed circuit boards and stack them parallel, stack them perpendicular. You can have uniform heights for the components. If you're packing things closer together, you're going to have to insulate them from each other with tapes and films. There's a lot of that in the lower right corner. A lot of yellow tape that's being manually applied. So there's a trade-off here between power density and labor cost. And shielding. Casting walls can be used to shield one area from another. That's what's being done in the right. Sheet metal, that's what you're seeing in the bottom right, or thin stampings like you're seeing in the bottom left. In a pinch, you can also use the PCB itself. If you have a spare copper plane on a PCB, that can be potentially used as a shield. You just have to do that very carefully. But the charger that you're seeing on the middle right is doing many of these things. So that is a 10 kilowatt charger out of the Volkswagen ID3 and 4. And you've got an AC filter on the left, DC filter on top right, and a power board in between. And there's connections being made over a cast wall that's acting as a shield, and there's a board-to-board connection. On that power board, I see three vertical boards, three vertical daughter cards that are doing the control and the housekeeping power supplies. And you can't see this, but under that power board is another board stacked vertical, a metal core board that actually has the power devices on it. So it's all, again, think Tetris, packed in very closely, which requires a lot of thought for how will it be cooled, how will it be assembled, and how will things be shielded from each other. So let's talk specifically about the semiconductor devices, because although they are small, how they are mounted can have big impacts on total system size and shape, and also how they perform and are cooled. So from a traditional point of view, it's more common to use through-hole devices like you see in the upper right. These are usually clamped down with some sort of insulator. In this case, these are clamped to a ceramic alumina sheet with some silicone thermal paste. You can have topside cool devices like you're seeing there, second from the top. Surface mount devices that either take heat through a circuit board using thermal vias, so copper plated holes, or directly using a metal core integrated metal substrate board. That's what you're seeing there in the middle right. Or you can have power modules either off the shelf or custom. This lends itself more to higher power chargers where, this approach can be justified, but these dies can be directly bonded to a ceramic insulated base plate that can give a very, very good cooling solution. There are lots of trade-offs here. These would be installed and assembled different ways. Some of these would have more or less options for second sourcing of the components, but the one I want to particularly highlight is actually common mode EMI. So there is unfortunately a direct trade-off where the better that you cool a device like this, often the worse the common mode EMI is, because the way that you cool a flat device to a flat surface is by having as thin of an insulator as possible and as much surface area. So essentially, you're forming a plate capacitor between two surfaces, and the more capacitance that you have, the more that the switching noise can be injected into that heatsink. So there are direct trade-offs here for sure. Moving from the mechanical to the electrical, switching frequency is what's often focused on, but there's a mixed blessing. If you increase switching frequency, you can shrink some of the magnetics, the inductors, the transformers, some of the capacitors. You also increase loss because each of those switching events has a fixed energy loss. So if you double the switching frequency, you increase or double switching loss. So there's always this trade-off between energy efficiency and density. And if you push too far into high switching frequency, even the density can start to plateau or even decrease again, because those losses as they increase can lead to increased cooling volume, larger heat sinks. So, and there are also diminishing returns. Sometimes that transformer past a certain point doesn't get smaller, it just gets more expensive. Now, helping to break this log jam is potentially using GaN or SiC devices. They can switch faster, they switch with less loss, and that essentially moves the curve. So if you look at that red curve for a traditional silicon device, and then look at that blue curve for GaN or SiC, you can increase efficiency, you can increase density, you can maybe do a bit of both. Hard to do both at the same time. Now that faster switching and faster switching rates may increase EMI noise, which may increase filter sizes. Even with silicon today, most of the chargers out there, at least in the DC-DC converters, are using resonant converters that already have low loss soft switching. So the benefits to SiC and GaN are somewhat reduced by that. I would argue that there are better uses for GaN and SiC. They have some unique properties which lend themselves better to different topologies to enable, for instance, bidirectional operation. Or particularly with SiC, there are higher device ratings, so you can have higher AC voltages with three-phase AC, or higher DC output voltages like with 800 volts. We will talk more about those later in the presentation. There are other things that you can do from a electrical point of view. One which gets some attention is using planar magnetics. As an example, what you're seeing in the top right is sort of how that works. So having a rectangular core, but rather than winding wire around a bobbin, you actually have spiral windings that are part of the PCB. PCB traces. There are some definite trade-offs here, but there can be some benefits, not just on power density, but also on the repeatability and the manufacturability. What you're seeing there in the bottom is the charger out of the new Tesla Cybertruck. And all of those gray rectangles in the middle and on the left are quite complex integrated custom planar cores that are integrating transformers and inductors. So that can lend itself both to smaller size, but also just to flatter surfaces that are easier to package and easier to cool. But let's move on to system integration. So this is a little bit more out of the box thinking, but the idea of, can we integrate multiple functions? Can we have a charger plus something else? If you can take some other external converters, some extra box, and you can put two functions into one box, then the system cost, the system volume and labor can be less. 1 + 1 can equal less than 2 in terms of that total cost and volume. You can delete connectors that are shared, wiring, cooling, mounting. So some of these things work better than others. I would suggest that integrating a auxiliary DC-DC converter is a win. Both the charger and the DC-DC converter need a battery connection. They're both power converters. The same is true for AC export, needed in some applications. Here, even more so because maybe your onboard charger has a connection to the traction battery and to the AC. Motor controller, it's possible this gets a little bit more complicated and there are some distinct trade-offs, but it's been done. Often you end up with a motor controller and charger that are both not optimized. The logical thought would be integrate a charger with a battery and or BMS. And this has some challenges because high power density for a battery charger is achieved by making it small and running it hot. And long life for a battery is achieved by keeping temperatures low and even, so not having hot spots. So integrating a charger with a battery may seem like a good idea on the face of it. It often is less than optimal. But looking at the charger with an aux DC-DC converter, basically a solid-state alternator for 12-volt battery and loads, there are different ways of doing this. You can just physically co-package two separate converters in a box, and there are lots of chargers out there which do that. Tesla Model 3 is one. You can actually try to share some of the components. It's possible to have a 3-port converter design where you share one transformer, which is what's shown with the red circle there. This looks good on paper. It can lead to some significant trade-offs, but it's probably falls more into one of those moonshot, high risk and high reward sort of things. You can reuse a whole converter. This is something that we do in one of our Delta Q and Z-Van chargers. We have a charger powertrain, which is reused as a DC-DC converter. There are trade-offs here. They can't both operate at the same time. And the input and the output voltages have to work out, but it works well in the applications that we use it in. And then finally, looking at AC export, AC from vehicle to grid, vehicle to load, in particular, like looking to run tools with a generator. Here again, it's possible to physically co-package two converters, but it makes more sense to make a battery charger bidirectional. So all the diodes need to be replaced with switches, so they're bidirectional synchronous rectification. There are changes that need to be made to the topology to be able to operate in both directions, and this is a good use of silicon carbide or GaN. For instance, the Tesla Cybertruck that you're seeing there has some a bidirectional charger that makes use of silicon carbide devices and some topologies that make it possible to both import and export AC. So we're almost at the end here. Just want to take a big picture look at, we've seen lots of options, different ways to achieve power density. So what is actually on the market today? This is not comprehensive, but I've looked at a selection of industrial EV chargers. Some are Delta Qs, some are competitors, some are from other industries, but the main thing is that these are all chargers where I have quite a good knowledge of how they are constructed. So there's a range here from very low power, 300 watts up to 20 kilowatts, 24 volts up to 400 volts, passive fan and liquid cooling, and some of these have integrated aux DC-DCs. I think the first thing that you'll notice is that power density increases very sharply with power. So if you're at low power, it's hard to achieve high power density. But somewhere around maybe 5 or 10 kilowatts, power density sort of plateaus. So what can increase power density? So they said power level up to maybe 6 or 10 kilowatts, and that it looks like things start to flatten out. DC voltage. The top plot takes all those points and plots them versus the output voltage. So you can see that the 24 volt chargers at the left are much lower density than the 100 volt chargers or the 400 volt chargers. Although again, things flatten at about 100 volts. Cooling type. In the middle there, you've got a few passively cooled lower power chargers in red, and some fan cooled in purple, and some liquid cooling in blue. And you can see that again, things stepping up to fan cooling makes a big impact. From fan to liquid cooling, maybe less so. And finally, in the bottom right, the points in red are chargers that also integrate aux DC-DC converters. And does this increase power density? Not on this plot. It looks like they more or less follow the trend. But I think if we looked at system power density, like looked at connectors, package space, wiring, that they would be increasing power density. The other thing to note is that none of these have any silicon carbide or GaN, to my knowledge, other than some of those 20 kilowatt chargers that have three-phase input. Coming back to the example that I talked about at the very beginning, what about that Volkswagen charger? So they doubled power density. They mainly did it through mechanical packaging and through cooling. Stacking PCBs, very careful shielding, insulation, and thermally potted magnetics. So it's built up layer by layer carefully, like Lego bricks or Tetris. But there's no secret sauce on the electrical side here, for instance. So takeaways at a high level. Even at the application level, looking at vehicle design, there are bottlenecks that you can remove to high power. Making sure that you have a sufficient AC source that you plug into, high enough DC voltage, and a cooling type that will let you reach the density that you need. If you're designing power electronics, you likely want to focus on the higher impact design options, which tends to be cooling and mechanical. There are things to do on the electrical side, but often there are better uses for SiC and GaN, like to enable bidirectional power flow or higher input or output voltages. And finally, it pays to get creative with system integration, to kind of literally think outside the box, particularly with integrating other converters like aux DC-DC or AC export. And that's what I have. So I think we will turn to Paul.
All right. Chris, thank you so much. A very interesting presentation. Hope everybody enjoyed that. We've got some questions now. We've got about 7 minutes left. We can quickly run through these. All right, the first question. In order to design the cooling system of the machine, would you recommend to make the OBC and battery selection at the same time?
Yeah, well, I mean, that's a great question. As a battery maker, or sorry, as a onboard charger maker, I certainly selfishly want to be part of the process early on. I think, practically speaking, from a system design point of view, usually the first thing selected is traction motor sizing based on what the machine needs to do, followed by battery based on its runtime. And then charger comes third or fourth, which is okay. I think it just means you have to look carefully at that liquid cooling loop. Are those devices all connected in series? And if so, how much flow rate has to go through that charger? Or is there some way to connect things parallel? That's an excellent question.
Okay. All right, next question. You described several ways to integrate a charger and auxiliary DC to DC converter. Can you explain the trade-offs of these approaches?
Yeah, so I'll just go back to that slide. So, separate converters. This is really going to come down to that sort of cost benefit, like how much impact is there versus how much technical risk is there. So having separate converters that are co-packaged is a totally fine way to go. provided that you can achieve the power density which is needed. And we see this in some automotive and some industrial EV chargers. Sharing the transformer, like a 3-port converter, I would suggest that you would want to do some fairly significant research and demonstrating and prototyping before putting this into a development program. That transformer design is going to be quite complex, and actually cross regulation is the biggest issue. So in this case here, what you're seeing is each of these converters is bidirectional. So AC charge or export, you can have flow to and from the traction battery or the aux battery. So how you regulate power only in the direction that you want is tricky. And then finally, reusing the converter. I think it's a clever approach that we've done at Delta Q, and we've had some success with. It only works with particular ratios of input voltage and output voltage. And it only really works if you don't need full power DC-DC while you're charging. We, in this case, often integrate a lower power parallel DC-DC. So those are some of the trade-offs there. Thanks.
Okay. We've got about 4 minutes left, so this may be the last question here. It's from Alexandrov, and he compliments you on a great presentation. He's asking, what are the challenges of implementing topside cooled semiconductor devices, and do you foresee them taking over in the future versus standard TO-220, TO-247 devices?
Yeah, so I'm just going to say, again, that's an excellent question. Maybe I'll just quickly jump back to that slide as well. So if you look at topside cool devices, and we've been following this closely, it can be an excellent solution, but there are a couple of gotchas. One is that it becomes difficult to second source the parts. So there are only a couple of vendors, a couple of big vendors who are offering topside cooled devices right now, and it's not necessarily the same package. Whereas if you use something standard like the TO or the D squared packs, you got multiple vendors, and when you're operating at high volume and all over the world and looking at tariffs and supply chain issues, having second sources is very critical. The other thing is just if you're building up topside cooling on a circuit board and then pressing it into some sort of gap pad, the stiffness of that circuit board matters a lot. So you may have to add stiffening or have a lot of mounting screws through that board, each of which will have a certain keep out area, and that causes the size of the circuit board to kind of blow up. So I would say yes, but there are definitely trade-offs here, but it's something that we are looking at closely.
Okay, I think we got 2 minutes left. Do you think you could answer one more in 1 minute for a bidirectional charger? How would the design be different for a vehicle to grid versus vehicle to load?
Yeah, so the hardware isn't necessarily all that different. Probably still a bidirectional charger, PFC, and a DC-DC converter. The differences may be more in the control and the regulatory certifications. So if you're powering loads, you have to, provide your own 60 hertz, 50 hertz sine wave. And you've got loads like, power tools or compressors, which may have large startup transients, which you have to handle. So there's like peak versus the continuous. And those loads can turn on and shut off without any warning. So you got to have quite fast dynamic response. On the other hand, if you're putting power back on the grid, there are now lots of regulatory concerns. The grid is quite stable. You just have to follow that 50 hertz, 60 hertz sine wave the way that a solar inverter would, grid tied. But there are definitely more safety certifications, and this is something that's particularly going to impact on automotive, where today those EV onboard chargers don't require third-party certifications like UL and so on. But if they're going to do vehicle to grid, they may need them.
Okay. All right. I think that's we've run out of time here. If you do have any more questions, you can reach out to Chris. So his information is here, his email, and you can connect with him on LinkedIn. But that brings the session to an end, and also the end of the first day of the 2025 Future of Electrification virtual conference. So to everyone that tuned in, thank you so much for taking the time to register and come and tune into our sessions. We really hope you found it educational and insightful. So we hope you can join us tomorrow for day two, starting early here in North America, but lots of great stuff, lots of great topics, and we do hope that we'll see you again tomorrow for day two. Thanks very much, everyone. Have a great day. Have a great night.